Hello. Uh, I'm going to carry on streaming some CTF stuff today. As you can see, I might have decided to take advantage of some of my toys. Yeah, I keep meaning to play around with these more, so we have lasers and fog and stuff today, because why not? Hopefully my microphone levels are a little better today, and the audio levels are a little better. I know the music was a little iffy last time, but yes. So let's get started. So last time we were working on the Cusco one. This was the first one I hadn't played before, but as I said before, it was, 2014 when I last had a look at these, and I managed to complete this one, so I was quite happy. Thank you. A sale. Sorry, small font on that screen. Yeah, cool. I'm glad that the audio is a little better this time. I know last time I was very quiet. Definitely messed things up there. But yes, so I'll leave that challenge. So this time we're on to Whitehorse. I have no idea what this one's going to bring. The last one was still stack-based, except it wasn't a simple Stack Overflow onto, say, for example, just like overwriting a flag. Instead, it was a Stack Overflow into the area where return pointers were stored for function calls. So the idea there was that we overwrote the return pointer so that we could gain control of the instruction pointer and then point it to whatever we liked. In our case, we pointed it to the piece of code which basically called the interrupt which unlocks the door. So moving on today, the firmware has been updated to connect with the new hardware security module. We have removed the functionality to unlock the door from the Lock It Pro firmware. So now it requires the HSM to actually unlock it when given the correct password. So if we just have a quick look in the manual. Oh, sorry, I thought I had zoomed back in on that one. And I scroll down a bit to, here we go. So they've got HSM Model 1, which is, I think, what we've been playing with so far. Or it might just have been the door lock. I can't remember which way around this one works. So if I scroll down a little bit, we can come and find the HSM Model 1. Here we go. Yes, so this has been what we've been playing with so far. So this is the Model 1, where the hardware security module has a simple interface which allows the MCU to test if an entered password is valid. So this is effectively, you call into the HSM and you get a yes/no on whether the password's valid. So that's generally being used to avoid us having the password check in firmware. So we can't just work out what the password is. So it's requiring us to actually do some exploitation. So this is what we've been playing with so far. And I think they're now moving us on to HSM Model 2. So this is the more advanced HSM. And this directly triggers the unlock functionality. So they've removed the unlock functionality from the firmware. So we no longer get the, I think it's interrupt 7.1. I think unlocks the door. In this case, it basically you give it the password and it unlocks the door if it's correct. So this is this interrupt 7e version. So I think that's the main difference here that we're going to be playing with. So let's take a look at what we got. So let's just break on main and continue. So that just calls into login. So I'm just going to step because, of course. Now this is interesting. They started doing this thing. I think they did it a little bit last time, but this time it's very much been a case of separating all this stuff out. It's starting to look a lot more like an actual compiled program. Before they were all a little bit sort of toy program. I mean, this is still pretty much a toy, but okay. So we've got this get SN call, which I think is getting the password. That's usually what happens there. And then we've got this conditional unlock door. So my guess is that the it's interesting that it's moving the stack pointer there. But yeah, so let's have a look at what's in conditional unlock door. It's going to be down here somewhere, or up here somewhere. Here we go. So interesting. So if we break on that, we'll just continue. We're going to put in a bogus password, so just password. And this always happens, it just breaks when we've done that. And we can see that password is on the stack again. So it is at 320E, I think. Yes, 320E. So if we just start jotting this down, 320E is password entered on stack. So we can step out of this, and we can step out of this one because this is just the wrapper around it. Okay, sorry. So if you're not familiar with what we're doing here today, so this is a Microcorruption CTF. So this is basically a series of embedded system security challenges related around binary exploitation. It's all based around the MSP 430. Let me just go and find the. Where are we? Here we go. So it's all based around this like MSP 430 microcontroller. And if we just go down to here we go, MSP 430. So the idea is that there are these locks, smart locks, and you have to enter a password to open the locks. First, we get a debug copy of the lock where we can test our exploit, like actually go through, debug things, try and find a vulnerability, exploit the vulnerability, and then we go into solve mode, which then allows us to enter a string either directly in characters or in hex into the real lock, so to speak. And the idea is that the game's operatives then go and break into the warehouse and steal all the good stuff inside. So the debugger here is just a web-based thing that interfaces us with the game. So there are different levels. So we've done the first, I think, 5 levels plus the tutorial. So here we got the disassembly, we got the register state up here, and the current instruction. This has proven useful when we've done stuff in one of the previous levels where we were actually calling into decrypted code, and the decrypted code then isn't visible inside the disassembly because it doesn't refresh. So you have to do everything through the current instruction thing here, and of course we've got the live memory dump. And it's all sort of console based, so if I take help in here, it tells me all of the different things that I can do with this debugger. And MSP 430 itself is actually fairly simple. Sorry, I'm just going to zoom out slightly because that's kind of huge. So you've got the the basics here. So it's got the concept of a stack you can call and whatever. They're using AT&T syntax mostly. I think it's either AT&T syntax or a variant of. I don't usually use that. I use Intel syntax. So this has proven a little bit confusing to me now and again. But yeah, so the instruction set is fairly small. So yeah, you know, you got your marv add sub and XOR, or there are some typos in here, as with all data sheets. Heretic with my Intel syntax is the best. And then these conditional jumps. So there's an absolute ton of conditional jumps and stuff, but that's like the whole instruction set. I say that I have actually come into some instructions that were not listed in here, and I had to go and look at the this MSP 430 reference guide, which like sign extend is not mentioned in here, but it's done a bunch in there in the actual code. But yeah, so that's effectively what this whole thing's about. So looking at this, we've got the password on the stack, and we're going to call into this conditional unlock door, and I think that's what's going to be doing the most interesting stuff. So if we look at the yeah, you see, so we've moved this stack pointer into R15. So that's 320E. So R15 now contains the, it's the first argument to this conditional unlock door. So if I step again, and I'm just going to note in here that 320E is pointed to by R15. So this is just basically initially just saving R4 because I think it's just going to be, you know, using R4 inside here. So yeah, DSB. Yeah. So that's just basically setting up setting up a stack frame kind of thing. So what do we got here? We got what's in R4 now? So R4 is now pointing to 320C, which I think is just kind of where we've stored the original stack pointer. As we see, it pops R4 at the end, which just returns... I guess that's actually just storing whatever was in R4. What do we got now? Ah, yes, of course. So, yeah, so R4 is becoming our new sort of like frame pointer because you can see here we're doing something with the stack memory here. So, pushing a couple of things, and then we're calling into the interrupt handler. So this is going to be, the interrupt dispatcher. So this interrupt dispatcher is taking 7E as the first argument, which means that it's going to be calling this new, where are we? Scroll up slightly. And by the way, let me know if the music's too loud or something. Or too quiet. So yeah, this is this HSM interrupt, and it takes one argument, which is the password to test. So that's going to be an R15. It's interesting that it pushed R14 and R15. I don't know whether this int call takes something separately, but I don't think it does. It hasn't before. Weird. But yeah, so we've got this call into here, and if we step, my guess is... Oh, yeah, that's not where it really wanted to do. I want to pop back here. So after this, we can see that R15, the low byte of that has been set to 0. And if I step again, we're going to get this SXT, which sign extends. So that's sign extended the R15 from a byte all the way over. So that's become 0. So we can see here that again the sorry, let's just continue, step, and then return. Oh, sorry, and then return. Now, I actually don't know how I'm going to solve this one, so this is going to be super interesting. That is interesting. Where is this jumping to? So, this is jumping F0 on testing R15. So it's tested R15 and it's set the carry flag and 0 flag is set. So this is going to jump to the bit where it says, that password's not right. So we know if I just continue, it's going to say no. So if I reset, continue to main. Now let's see what happens. Let's see what happens here. Where are we? Let's see what happens here if I continue and put a big pile of garbage in here. And then just continue. Now you can see that this stack memory has definitely been overwritten here. But I'm not sure how much of that's going to actually help us. So let's find out. So we're going to step. And we can see that... Now, this is the interesting bit. Oh, sorry, didn't need that. Let's hop out that. Now, here's the interesting bit. You see how it's... see how on the stack we're jumping to here? When we return now, what's going to happen? Well, EIP is now at 41414141. Which isn't that useful in of itself. However, I'm fairly sure that the if I were to then replace this stack data with opcodes and then jump to the stack data, I could probably call int which one is it? Int 7f, and it just opens the deadbolt. So let's try assembling int 7f. Oh. Well, that's interesting. Of course. So instead, we actually have to call the interrupt, the interrupt trap. So there is a function on here called int. I could just call it int actually. Where is int? Here it is. Yeah, it calls this hash 10. So I'm not really sure exactly what's being set up here. So let's no, I think it's 7. It's 7F because 7E just sets the 7E is the HSM2. But what I want to do is bypass the HSM2 call and just go straight into 7F. And effectively putting shellcode. This is the first time we've put shellcode on the stack and called into our own shellcode. Before we were able to just abuse what was there. So I think what I really want to do is if I just reset the CPU. We've got this breakpoint set here, but I'm not interested in that. That's the one I want. So if I just continue. Oh, that's interesting. Why didn't it ask me for a password? Oh, of course, because we've got an int first. So if I just continue off that. What's going on here? Oh, there's an int on every flipping... Ah, that's a thing. So... Okay, so... Actually, I don't want to do that. Instead, I'm going to look for the call to the int that I want, not in getchar. I want to look for... Although, actually, I could have just used any of those. What I'm trying to do here is I'm trying to look at what the setup is for calling into this interrupt vector at 10. So I'm actually looking for... it's conditional unlock door that's going to do the one to 7F. Although, actually, I think I can just... So, yeah, this is it. I could just push 7E on the stack and then call into that. But then the problem is that it kind of messes up my stack addressing. Because if I push something, and then it's obviously going to miss the modify the stack pointer, and then I have to calculate what the stack pointer is going to be. And I would rather not have to do that. If instead... I can just directly do the interrupt as if I was calling into int without actually calling into int. That would be quite nice. So if I just reset, continue, put in a bunch of garbage, and then hit send, then continue. Now we get this call to int. So if I step into that, so we got 7E is on the stack, so we step into that. So we do some stuff with the stack, blah, 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 blah. What I'm interested in is, before this call, where is 7E? So 7E is in R15. Oh no, is it in R14 or R15? It's hard to tell which one this actually wants. I'm going to guess it's R14 that it wants it in, because R15 is... It's on the wrong side of that, which is... Then it's... Why is it setting these? Maybe the interrupt needs a bunch of this setup that I don't want to do. So maybe I can just, like, do it. You know what? It's actually going to be more fun to try and calculate all the stack offsets and stuff with a push in there. So let's see. What we really want to do is push 7F, because we're pushing the... we are pushing the interrupt type that we want to call. And then we're going to call, and I'm not going to put in int because it's not called int. It's 4532. So if I assemble that, yeah, getting that. So this is the hex that we want to load into there. So what I'm going to do is just reset this again. Or did I already just reset it? I did just reset it. So I'm just going to continue, and then I'm going to enter some hex encoded stuff, and I'm just going to put some buffer bytes either side just to see where I can see them, and then send that. So what we can see here is actually that, so it's 101207, and you can see here that in memory it's 101207. Now that's not going to be good, because if you look here, the first byte of that instruction is actually misaligned. So we already know that that's going to be a problem. So instead of what I just put in, how many did I put in? 1, 2, 3. Oh, I put 3 in. Well, that wasn't very bright, was it? So let's try that again. So let's do 41414141, and then 41414141 on the end of there. So now we can see that we got this data on the stack, which is the password. So that's 4141, 4141. And then we've got some aligned instructions that we want to go into. And then we've got 4141, 4141 again. Now, if we just continue. Interesting that that just happened and it didn't get to there. So that means that we didn't put a long enough... we didn't put enough garbage on the end of it to overwrite the stack. Let's try that one again. There we go, let's just try that. Now, if we continue, instruction address unaligned. That's fine, because that means we now know that at this offset, we managed to overwrite EIP. Probably, actually. So the next thing to do is work out where exactly in there it's pulling our new program counter from, the instruction pointer. So if we reset that again, continue again. Now, this time, instead of putting this like 414141 over the end of it, I'm just going to put a space just because it's easier for me to see what's going on here. I can do this. So if I do this, in fact, I think it'll actually just accept this just fine if I put some spaces in there just to separate stuff out. Haha, which it will, good. Right, so what's going to happen here is when I continue this, you get this instruction address unaligned. And if you look here, it's pulled from 4645, or rather 4546, because the endianness swaps the bytes around. So we can tell now that at the offset 4546 is where it's going to set PC. And then we want to bump that to call into here. I think, no, here, sorry. So which would be 3212. So let's just jot that down. So offset. Oops, that's not the word offset. That says offset. Offset is at 4546, and our code is at 3212. So now what we want to do is have this redirect to 3212. So if we then look at if we then look at our payload, so our payload is this, and we know that somewhere around, where is it, 4546, we know that here is where the instruction point is being pulled from. So it's, oops, so it's this 4546 here, and we want to redirect ourselves to here. There. So what we want to do is swap these bytes out 4546 for 3212, but we need to flip the bytes because of the ending in this. So it's actually 1232. I think. Yes, because that's 3212. And there's our code. So let's just give this a go now. And let's reset. Let's continue. Let's put that in and send it. And now if we just look for where was the ret that was getting exploited? I think it's back up in login. Yeah, it is. It's here. So if we continue. So we can see here now that the stack pointer is about to be shifted. So we go step, and we can see here that 1232 is now on the stack. We step again, and it's moved to 3212. 3212 is our code. Our current instruction is push 7. Interesting. Now, it should not be push 7. It should be push 7F. So where did we go wrong there? Is this an endianness issue? It might be. What do we got here? So what did we put in? 1012. 1012. Interesting. Why did it do that? Because that should be... There is no F in here. That's also interesting. That would be why. It was not assuming the correct bytes there. So let's reset that again. Oh, that's not the right one. So I had forgotten to put in the hex markers. So that's now our code, and that's now our payload. So now let's continue. Pop our payload in. Continue. Now we're at this add, and we can see that we're about to pop 3212 back into the PC, which we can see, and now we got push 7F here up in the current instruction. And we step again, and it's going to call into 4532. Interesting. Load address unaligned 3295. Well, isn't that strange? What's 3295 about? I don't know what that is. Where's this from? I don't know what that does. Sorry, what that is. So, PC is at 3216, which is here. Which is this 9012 blah 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 blah. Oh yeah, so this is this... Ah! You remember I said that the push was going to mess things up? Well, guess what? Just got pushed onto the stack. So, I think this has shifted everything. You see here, it's like shifted the shifted all the data. So what we actually want to do is move the stack elsewhere. So if we move the stack down to say, we move the stack to before. So let's just say we move the stack to like 31F0 or something, or 31F2. So marv 31F2 SP. So now we got this. However, because our payload is now going to be longer, we know that... Oh, that works perfectly. Because this is where... Wait, is that an odd number of bytes? Oh no, there's a space there. So we're actually at this exact point. So we've used all of our stack space here. So our new payload is still going to be this. But we now no longer... Oh, actually, this is not true because I have another 4 bytes here and I can shift things down. But let's just try this. Not that one. So let's just reset again. Continue. Drop the payload into there. Continue again. And again, we're going to stop here. So now we're going to step. And the first thing we're going to do is, we've still got the right offset for pulling in the stack pointer, because if we step now, we can see that sorry, not the stack pointer, for the program counter. So we can see it's still gone to 3212, which is still the start of our payloads. And we can see here that it's found this push 7F. So if we step that, oh, I pressed the wrong, oh no, I did press the right button. Well, now we get this again, we get this load and align thing. Okay, so we can't continue anything because the load address is on the line. I'm not sure what that means though, 3295. Because there's nothing here that's at 3295. 3295, it's just some garbage address that doesn't exist. Oh, of course, I'm being a moron. I put these backwards. I need to move the stack pointer before I do the push. So now let's swap this out. Reset again. Continue. Send. Continue. Okay, we're at the same point. I've got a ret. Now, we're moving the stack pointer. Well, that's interesting. You see that? Oh, you know what it is? I don't think it thinks these aren't constants to it. I think that's why. Because I forgot to put the hashes in front of it. This is why it's confusing to me, because they're using a weird syntax that I'm not used to. You can see this has changed now, I think. Yes, we've got this FOOB to FO09 here. These are memory addresses. That's why it was failing. So this should now be loading the correct. So in fact, it may be that we don't need to move the stack pointer at all, but we'll try this for now. And we will continue. And we will do this. And we'll do this. Again, we're at this point. And EIP is now moved to... I keep saying EIP, I'm so used to x86. The instruction pointer is now at 3212. We've got this mob. This actually has now executed properly, although it still has moved the stack pointer to 0. I don't know why it's done that, but... Now where's the stack pointer? Let's move the stack pointer over here. Well, that's weird. It's underflowed the stack pointer, but whatever. I think that's probably fine. And it's going to call into here. And now we're backing in. So let's see what's going to happen here. Step. And load address should wrap. So that messed things up. So I don't know whether we actually do need to move the stack pointer. So let's just try this again with without this like mob here. And let's just go back to our old approach, which I think if I just take this and then put it here and then and then got this in. So this is the new approach. Or the old approach, but done properly and not messed up. So continue. This in. Continue. Again, we're loading the right pointer. Where's the stack pointer though? So the stack pointer is way after our code, so I think it should be fine. And the current instruction is now call, so step. This looks like it might work. And there we go. Solved it. Fantastic. So now if we put in solve, we can drop in that same input, send, and we have solved the challenge. I am happy with that. Deserves a drink. Ah, lovely. Right. This is like reading pen test reports for me. Not pen test reports, but vendor responses. We have re-implemented much of the code according to our internal secure development process. Particularly the whole, like, we have received unconfirmed reports of security issues. Like, unconfirmed reports. We take your security seriously. Interesting. Okay. So what's it going to do this time? I wonder whether this is where they're going to start, like, you know, enabling depth. Ah! I mean, you can see here they're doing Stracopy and memset and stuff. That's interesting. So if we just continue, I'm just going to do the usual thing of putting garbage in. Okay, so we got a much bigger space of data here now. So let's just reset that and just try and put more in than 64, because I think it was 64 that they said they got. So just that's a lot of garbage, and it cuts it off. So you can see that this buffer is actually quite big, but the it's very much just cut off at this. Yeah, it's what? Oh, it's not 64. It's something else. 16, 32, 48 bytes. Interesting. They're still putting it on the stack, which is interesting. But it's saying the password is not correct and it's not messing anything up. So I think this one might be a little bit more challenging. Oh Christ. Memset implementation. Just huge. Ridiculous. Oh, hang on. You see this? This init stack and lower level init. I think it's been overwritten. At 440E. We've definitely overwritten some program code here. That's interesting. Very interesting. And we've got I didn't spot that. We've got instruction address unaligned. So we've actually moved to 4147. So what is garbage printed into hexadecimal? 2 hex. In case anybody doesn't know what tool it is that I'm using here, it's CyberChef. It's this kind of awesome little drag-drop thing made by GCHQ. They seem to be doing a lot of good stuff for reverse engineering these days, but yeah, it's basically you can just drag-drop things into like a little recipe, put code in, put data in, and you get data out. It's quite useful. It does a bunch of like clever encryption and forensic stuff as well. So 4147 actually is probably the first one here, because if it was this one, 4147 here, well, one, this is, oh no, it is aligned, but it's actually 4741 because of the endianness, and we've got 4147 here, so I think it's going to be this, or at least one of these. So somewhere along here, this gets poked at. So let's reset, and I think it's going to be probably quite similarly messed up before, like this add 10 SP thing. So if we just continue, put in a bunch of garbage, and then send, and then continue. And where's the stack pointer? See, the stack pointer's here, so it's definitely, we're definitely overwriting the stack. So it looks very much the same as before. I wonder, though, whether... See, there's a thing somewhere around here on these interrupts. Here we go. It's got this interrupt 10 and interrupt 11. I don't know whether we're quite on this depth bit yet. Maybe we are, but let's find out. So let's just reset again. I know now... Hang on, before we do that, actually. 1... 2. So it's on the third instance of the word garbage 1. So let's just start a new one here. So input is this. Sorry. The input is this, and then what we're finding is that this is the offset where PC is getting overwritten. Right. So if I now reset, you see how this like init stack and low level init stuff is here? Before it was getting overwritten weirdly when we're putting garbage in. And what's this stop prog exec as well? It's interesting. Yeah, I'm not really sure what's going on with that. I don't know why I can't just do exactly the same trick again. Maybe I'll just try doing exactly the same trick again and see what happens. So, I wonder whether when it's setting up the stack now, maybe it's doing some clever stuff with enabling dep, but let's find out. So did I put a break on? Yes, I did on that. So let's try and just exploit it in the same way. So we can see here that we're about to overwrite this point. So let's just take this as our new input. And we want to convert that to hex because we're going to start putting things in hex. So it's that. And I'm just going to take the spaces out of that because I don't want that many spaces. In selection. Right. And we know that it's the 4741, this one here. So we're going to say that this is the point where we want to put a PC, which I guess we're going to put... That's another thought. Is the stack in the same location every time? Maybe it's not. Because that's the other thing. There is a... If we look in the manual... Interrupt 20 pulls a random number out. So it could be that they're randomizing the stack location, but I am guessing here. These are all things that I expect are going to happen at some point. So where's the start of the stack? Or rather the start of the garbage data that we put in. So let's say we've 43EE. So EE43. So let's reset again. And we're going to continue. And we're going to enter this in hex. And we're going to continue. The stack's in the same place, 43EE. So if I now step, yeah. So the performance, I keep wanting to say performance counter because PC is performance counter in so much like .NET stuff that I do. It's not a performance counter. I suppose it is. It's how many instructions have been executed. Sort of. If all of your code is linear and never jumps anywhere. Right, so it looks to me like we could just do the same thing as before. Where's this int? It's just here again. 454C. So now we want to assemble some code again. 4.5, and this now becomes 4.54C because that's now where our thing is. So that's now our payload. So I guess we can just put it here. And then how many bytes is that? Sorry, that is 24 characters. So that's 8. Wait, really? That doesn't look like 24 characters. It isn't. That's because I read the wrong word. It says col, not cell. Okay, so that's 16. So that's the same as that. And then we just got this again. Which again, I'm just going to... It's that one, and then just... how many have we got? That's 12. That. So this is our payload. This is some padding. This is the PC overwrite, and that's more padding. So let's try resetting, continuing, dropping this in, continuing, and we've got this again. We step. Ah! Now you see what's happening here? It's jumped to the stop prog exec. Because these pages are not writable. These pages are not executable. It's enabled dep on the stack. Somewhere in here, I can't say where exactly. But I can cheat and copy all the assembly out. I think I accidentally set a breakpoint as well. I want to do that. So if I just put that in here, I am looking for hash not x. Now where is this? It's 10. That's adding it. That's doesn't find anything. But I think dep's been enabled. Because you can see here that it's going to this stop prog exec thing at 443C. I also don't see anything in here. But do you remember when we first tried this? It overwrote some of the code up here. So that's interesting. The other way to go about this is just basically do a ROP chain. Because we can control the performance counter. I keep saying performance counter. What's wrong with me? We can control the program counter. And we can control... That could work. So... if we just reset this, I just want to see where the stack pointer is at the moment. The stack pointer is when we do this. Not that. Idiot. That. And we continue to the point where we're about to do the... Hey? I thought we had a breakpoint. Oh no, I removed the breakpoint by accident. Right, so at this point, where's the stack pointer? The stack pointer is not... Oh no, it is within... No, wait. Well, now I'm confused. I think I just worked out what's going on. I think I just worked out what's going on. I think there's absolutely nothing in here that does depth. I think it found a null byte. That's why there's the mem copy thing in here. Struct copy. Because it needs no null bytes. And guess what's in my payload? Right here. Null byte. Can't have that there. So, we need to come up with a way of encoding this without null bytes. So, instead of this, I'm not sure where this null byte comes from. So let's reverse this process and disassemble it. And we can see here that it's the push 7F. Because it's pushing 7F00. Yeah. So instead, we need to find a different way to get 7F into the as a stack variable, but without using that push, without using something that's got a null byte in it. So I think a way to go with that is probably using something like the bis instruction. So if I were to do something like mov hash 7, I don't know, let's say into I don't know, let's put it into R1, who cares. That does not create any null bytes. Now, if we were to then, not this, what's the instruction that I was looking at? Sign extend, SXTR1. Again, no null bytes. I'm not sure how that works in terms of the other way to go, actually. I don't know how well this will work, but it's another point. We just do this again. What's the register state? Can I steal anything out of any of the registers to make this easier? Not really. I was hoping I might have something like FF00, but that'd be too easy. Oh, I mean, the other way to go is just I think they have like mov B. Is that a thing? Or something like that? I think I've seen it somewhere around here. Yeah, we get this mov B, which just moves a byte. So what if we were to like mov B, and it's like at SP, is it? How that works. It's in a manual somewhere here. Yeah, it's like reference RX. So I think it's just at SP R1. Is that a thing? That's a thing. So we can move something that we've got in the stack. So we can just have 7F as a byte. And then what do we want? We want to push it. So push R1 and then call that. That has no null bytes. The other thing we can do here is, I think it's like, yeah, like that plus, yeah, I don't really know how this works. Maybe it doesn't want the hash. Maybe it's just that. Nope. Doesn't like that. I think they want it like this, which is this weird style, which is not what it says in there, but... yeah. So that, as usual, the datasheet's wrong. So this, I think... but then we got this null byte back. So it has to be actually at the stack pointer. But that's fine. I think that's fine, because we don't jump directly to the stack pointer. And we've got some padding here. So if we were to take this shellcode, which now no longer has a 0 in it, and if we change this to 7F, and then we put the padding here, because I think this is the same length as this, isn't it? It is. So we can actually just move the padding this way. Like this. And I'm actually going to split it in half, because no reason whatsoever, but I just kind of like having a bit of padding. And then we put in a stack pointer, which will not be this anymore. It will be, because 43EE was here. So we actually want to move that plus 4 bytes, which is going to be 43F2. Oops, wrong button. I think. Programmer mode. Let's move this into Word. And it's 43E plus 4 bytes is 43F2. Yes, I was right. I thought it was. So I think this now should copy in and shouldn't get nabbed by the mem copy. So let's just continue. Put it in. Continue again, because we're going to break on here. So where's the stack pointer? The stack pointer's here. Now that's interesting, because the stack pointer's in the wrong location for what we want. Oh no, it isn't. Sorry, no, it is not. Because, yeah, I thought we'd mess that up. Because, of course, the stack location after the ret... because if we do this... See, look, the instruction address is unaligned. Wait, what? Well, that's weird. So we've got the 7F41. PC is like F243? Oh, yeah. Oh, I put this backwards. Duh. Indianness. Everybody loves it. I'm lying. So now we're at 43F2. Which is the wrong location. Of course it was. We're 2 off. Because that's that 0112, which is, if we look in here... Wait, 0112... Oh, this actually... Sorry, I didn't realise this. This actually assembles as 4141. So this is actually in the right location. Yes, because it's MOV... Although we've got MOV B SP SP. Which is not what I asked. Oh, of course, because R1 is SP. R0, R1, R2, R3, R4. I forgot that those are kind of weird general purpose registers. So let's swap that round. I'm going to make this go in, I don't know, R9. Don't think that makes any difference. So now if we swap that in our payload to here. And then reset. And continue. Pop that in here. Step. Oh no, continue. And then here we are. So we step again. And we're at 43F2. Here we go. We got MOV SP R9. Now, that is not what I wanted, because I don't want it to just move the stack pointer into there. I actually wanted to move the memory at the stack pointer. So I actually typed that wrong. So it should be that. Nice. I'll get there eventually. This is the thing about exploitation. It's all trial and error. Here we go. So, we step again. We now know that the performance counter is at this 6941. Again, nice. Move the contents at stack pointer, which is here. Which is the wrong location, but screw it. We now know where we need to move it. In fact, it should be... Because this is the thing. I've moved it to here, thinking for some reason that the stack pointer was going to be here, but it's not going to be there, because it has to be immediately after this address. So it'll actually be here. So if I were to... I think it's... I can't remember the thing for this. It's right... It's just like let 4400 equal 7. What do we want? We wanted it as 7F 41? No, the other way around. 41 7F. Then if we step, now what's in register 9? 7F. That's perfect. So we want the 7F in there. So we push R9. And we unlock the door. Fantastic. So now we just need to actually make that work live rather than with me editing the stack. But that's just because we knew it needed to be there. So we reset. And let's just pop this in. Continue. Continue. And we unlock the door. Solve it. And we unlock the door. I'm pretty happy with that. I am going to BRB. I'm just going to grab another drink. So, see you in a couple of minutes. I am back. Let's have a look at this challenge. By ensuring that passwords are too long will be rejected. Ha! Oh, you know what I should do? Not leave that on. There we go. I don't want to leave my fogger on continuously and get choked to death by fog. Right. What's going on here? Well, that seems to get into the buffer. Okay, so let's just reset again and put in a lot of garbage. Excuse me. So we can see here again. What's going on here? We've got all of this stuff in the buffer somewhere, and then I'm just going to continue and see what happens. This is wrong. But again, the stack pointer is at this thing, and we overwrote a bunch of stuff here quite clearly. Or did we? I can't really tell. Ah, but that's interesting. Because it's jumped to this like stop prog exec, but I don't know whether that's just because it got to the end and said, no, it's too long. So maybe we need it. Ah, I think this is going to be one of these ones where we need it just the right length. Because the 0 byte here is going to do something, I think. I think they're going to mess something up. So what was the length here? We got 64? So let's quickly just in here do 41 times 64. Reset and continue and pop that in. And it's saying it's too long. Womp womp. Maybe it's enforcing this 8 to 16 thing. Unless... You know what I think it is? I think it might be an integer overflow. Where's it getting this? Is it in getSN? Is it testing that the password's valid first? Yes. What? So it's doing a password validity check first. Which is why it's strip copying it over to the... So it is validating, but only after you've already tested the password. Now, then that's interesting, because 2C11... So where's test password valid? Yeah, and you can see, look, all of this has been overwritten with garbage. Where was test password valid? There it is. It can't be an integer overflow actually, because you would need enough memory space to do that. And there isn't on this because it only goes up to FFF0, so you can't overflow the value back round, I don't think. Not in any sensible way. What's going on here? But it's struck copying this onto the stack for some reason. So if I just reset again, continue, put some garbage in, continue. Here we go. So where's the stack pointer? Stack pointer's here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then you got this. 0, 0, 2C, 3C, 4, 4. Now, if I continue, yeah, it's definitely overwriting some stack values here. So there's something potentially that's going to allow us to you know what I just realized? They're storing the value, the length value on the stack. So if I continue, look at this. There's 11 SP here. So read. I hate this. It's. Yeah, so it's this 43FD, which is what, ED here. So that means we actually control the size value. So I think we can almost take the same payload as last time. Like, what happens if we just put this in, and then, yeah, let's just do this, and then just, let's just do this, and then reset. And continue. 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 Here we go. So it says the password is not correct, but that doesn't matter because. So we want 11 bytes after. So it's read SP plus 11, which is actually at the 437F. So what we need to do is rejig our payload. Where was the 437F? Oh, that's actually here. I don't think we need. Oh no, we do need that. But that's interesting because we can just then move our payload around. So if we just, I don't know, do that. And then we can just put another 4141 here. So now let's see, now what was it? It was comparing this to 2C, I think. And it's comparing by byte, which is important. So where was it? It was the 437F. So we moved it across, so I think that can now be like 2B. And I think this actually works, because if we just reset it, continue, do this, continue, and when we get to here, read SP plus 11. Ah, okay, so we haven't quite got the right location again. Did I do this kind of backwards, or what? Or 12B? Oh, no, 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 that is correct. So if we step that, what do the flags say? The carry flag is set. So, okay, I did mess something up there. So I think that needs flipping around. But I don't know which of these it is actually reading. So it might be that. I'm going to just like put that in because not right. Do it that way. So that way I can see quite easily. Okay, so we're going to continue. Try putting this in. Continue again, continue again, continue again. So if I read, is there not a like a read byte? Ah, okay, read C bytes. Okay, so it's read. Oops. SP plus 11.1. That still didn't do what I wanted it to do, but okay. Why is that reading 4.1A? Oh, okay, so it is reading this previous... It's reading here, which is not where I want it to read. I actually need to step everything back by 2 bytes. So if I remove these two, and then just... Actually don't need to really add more padding on this end, but that should be fine. So let's reset, continue, drop this in, continue. I'm going to just knock these off because I'm not using these again, and continue. So if I now read SP equals 11, we get this 2B41, but it's only reading 1 byte. So if I just step, now we have bypassed the check here, because before we were seeing that the carry flag was set, but now it's not set because it's reading this byte that we put in. So now what we need to do is we need to get to here and find out... Oh, okay, something else just happened in there and stopped the program execution. Oh, of course, it goes to here, doesn't it? That's not very useful. Wait, what? Why did that just say password's wrong, too long? Now I'm confused. So if we reset and just try a really long password. We end up here, and it does do this. This password is too long, and it does stop. So what it's doing here is it's going call prop. So we can bypass the check, but because it's branching to the stop proc exec, which is where here, and then it's calling to 443C, which is here. Oh, it's just effectively like a loop. But I think that's not really all of what we needed to do. So I'm not sure, really, exactly how we... Because the thing is, this ret never gets hit. Unless the password is correct. So actually all we need to do is bypass test password valid. That's the thing. I think test password valid just looks to see... Are they doing mem copy in this one? Ah, yeah, they are doing strict copy. I don't see anything in here. How is this testing the... I'm not sure how this is testing the password, you know. Where are we? Oh, let's reset. So... it's moving... Where's R4? So R4 is pointing at 43EA, which is actually inside of our... Okay, so that's 0 is something on the stack. Oh, so this is just the stack setup. So 7D. Oh, is this actually just like the old thing, or is it? was the interrupt? 7D. This is the old HSM. That's interesting. So it's going into the old HSM, checking the password of the old HSM. Yeah, I don't care about that. And then so this is just setting R15 based on whether the old HSM... Oh, this is the old style HSM then. So this is using the HSM version 1. And it has an unlock door call here. So we don't need to do anything as quite as funky as before. We just need to bypass the length check. Why is the length check 2C though? Where's that coming from? That's interesting. Because of course, if we step here, we can see that the 0 flag has been set. And it's saying jump if 0, which is going to be jumping into... That's not correct. But what's this stack pointer variable? It's not x11sp. It's super confusing to me. Oh, excuse me. Yeah, so we can see that it's going to here. So okay, so we know that this is being set somewhere. So this is so let's just, I think we need a new one of these. So we know that SP plus 11 at the length compare check, the address of that is always going to be what? 43FD, right? It's going to be 43FD. 43FD, I think actually there is a function here, a command that lets you, here we go, track the given register, and that's not really what I want. I want to, what I really wanted was to trace, oh, excuse me. I really wanted to break when that memory got hit. Yeah. They don't have memory breakpoints. Just weird, this MOV, this 11SP thing is a little weird to me. I don't know where that's being... Like, it's quite clear that I've... What is login plus 60 here, actually? So if I just let SR equals 0, because JEQ just checks for, so JEQ is just, JEQ would actually be for the 0 flag set, wouldn't it? Yeah, so this jump if the 0 flag is set. So I actually can't remember what that. So that's the carry flag. That's the 0 flag. Okay. So actually, really, what we want is to have that set to 2C, don't we? Because where did that just go to? Oh. Oh. Ha. Okay, that's more like it. So what I didn't notice was that actually, this flag here, this 2C flag, jumps us to the end here. I thought for some reason this was jumping us somewhere else. I don't understand quite why I thought that. So that was definitely an oversight on my behalf. So I think we can basically just carry on using this thing here. So let's just let's do the old pattern thing. Where was it? Did I save that somewhere? No, I didn't. So let's go with 4-1, 4-2, 4-3, 4-4, 4-5, 4-6, 4-7, 4-8, 4-9, 4-A, 4-B, 4-C, 4-D, 4-E, 4-F, and 5-0, 5-1, 5-2, 5-3, 5-4, 5-5, 5-6, 5-7, 5-8, 5-9. Right. So now if we reset this, I don't know why I just did that. Continue. Enter some hex input, send, and then what we want to do is it needs a breakpoint on. We've got some breakpoints set, but that's not what I want. Don't care about that one. What I want set is a breakpoint on the login function, which is here, and I want it on this. So we continue. We get to here. Oh, I love this tune. Sounds like Uplink. Excuse me. Right. So read SP plus 11, and we want to read 1 byte. So we now know that that's actually at 5253 in the offset. So if we go here and we look for 5253, this is right here. And this is getting read by this compare instruction. So what we actually want to do is here, we want to put in this 2C flag. It needs to go here. So if we take this and just turn it into a bunch of, or actually no, let's not do that. No, we will. We will take this here because we want to know everything before it. Because we're going to be doing EIP overwrite later, so we want to know where we can actually get to with this. Afterwards, we can probably just... Although, if we just do this for now, I think we might actually need 5A, 5... We might need a bit more in here, so I'll just pad this out. C, 5D, 5E, 5F. So this is a cool little trick you can do just when you're doing any kind of binary exploitation. You just put in a pattern that helps you identify the exact location in a buffer where some data is being read from or like written into. It makes it a lot easier to spot stuff. So you can see how this has now got this 2C flag right here. And it's because it's a compare byte. And I think the first byte it is actually going to compare is this 5.2. So let's do that again. Let's reset. Continue. Put in our payload. Continue. Now if we step, we should find that the 0 flag has been indeed set, which gets us to the add SP. That's where we want it to be. Okay, so now where's the stack? So we can see here that it's actually in the 5354. Which means if we look here, it's actually landing afterwards, which makes a lot of sense actually, because we just added 12 to it and it was reading plus 11. So it's a good job we did put this payload afterwards. So here we go. So we got this thing here. So the next thing that we're actually going to do is just double check whether they've got the strict copy. So they have got the strict copy, so we can't use a payload that has null bytes. So we can just use this payload again here. So what we actually want to do is, if we put this payload in at the start, So then we just need to go up to here. So we need a bunch of padding bytes. Did I do that backwards? No, I'm just an idiot. There we go. So what happens here is we got our payload. We've got some padding. So this will be the executable code that from here moves the data at the... that's another point. Where's the stack pointer on at this point? So that's where the stack pointer is now. After RIP, it'll be 5556. So what we do there is in this 5556... Yeah, so it'll be 2C. Wait, hang on. What am I doing here? So this is 5354. This is going to be... So if I step once, we can see that 5453, which is obviously 5354, but in the opposite, with the endianness, the bytes get swapped. We can see that we've overwritten the program counter. So this is where the EIP is going to be. So we've got basically, if we break this down, we've got some exploit code on here, which is going to load 7F. So we can't just do push 7F because push 7F contains a null byte. So we want to pull 7F from the stack. So what we've got is we've got basically a copy from the stack, a single byte into register 9, move register 9, push register 9, and then call into int, which then calls interrupt 7F, which then unlocks the door. So what we've got here is we've got our payload, we've got padding, and we've got the flag byte, which is just this weird little trick byte that for some reason, the application just uses to skip the stop program execution thing. Then after this, we've got... I'm just going to change that to like this because I can't fit any more text there. Then what we're going to do is this is going to be where the program counter gets set. So we want to set that back to the payload, and we know that that starts at here, which is 43E. It's not E, it's E. Why is my brain not working? It's not 43EE, which is here. It's 43E. C? Why am I? I'm getting tired. 43E minus 2. Yeah, 43EC. So this then becomes EC43 because, again, endianness swaps the bytes. So this is program counter getting set, and then I think after that we want... so then the stack will move... the stack pointer will then move across one, which means the next byte needs to be 7F, which is because the first thing the payload does is pull... pull a byte from the stack pointer, but this is where the stack pointer will be after... so after the rep, and then we can just put some padding on the end because why not? So let's try that. Reset, continue, drop this in, send, continue. So if we step, we can see that we bypass the check. That's good. So where's the stack pointer now pointing? It's pointing at 43EC, so pointing at this bit of memory that has 43EC in it. So when we step, 43EC is now in the program counter, which calls morph SP R9. Now SP is in fact pointing at that, so we can see that R9 now has 7F in it, and if we continue, that's interesting. So instead of working... Oh, that's the wrong one. Instead of working, it did something else. Did I put the wrong... Did I put the wrong interrupt in? So I thought I was doing an int 7F. I did indeed just put a 7F in there. What? So hang on, let's just reset this. I wonder whether the 7F is getting messed up somehow, so let's just continue. Yes, this is hex encoded. Continue again. So we can see that this gets bypassed, that's cool. So we step there and we step there. The first thing we got is Marv SP R9. So where is R9? Sorry, where is SP? So that's here. So if we step, first thing that happens is gets R9 in here. So that's 7F. So we step again. Oh, it's because we put the wrong damn address in for the it's the old address for int. Int is here. It's actually 4594. So that's why. So that's the difference. I was just jumping to the wrong location. I was wondering what was going on there. So that is now the proper payload. So if we reset this, and continue, we should find that again it bypasses, again it bypasses. We've got the ret. We move R9 in from the stack, which gets us 7F in R9. It then pushes R9 onto the stack, so that's that. And then when we call into int, we should unlock the door. Fantastic. So I am now going to solve that and put that in. And we have solved that challenge. I am very happy. So we've done Johannesburg now. It's getting kind of late, so I think I'm going to call it. So thanks to the folks who are hanging out, and I will see you shortly. I'm not quite sure when my next will be. Let me just quickly check my calendar. What we got going on? I might stream this weekend. I don't think we've got anything major going on this weekend. So yeah, I might do a bit more streaming this weekend and see if we can move on to Santa Cruz and Addis Ababa. I don't know how many more I'll do before I start getting into techniques that I am not familiar with at all. I think I can go as far as, you know, some basic rock chains maybe. But once we get into like heap corruption and stuff, it's a little bit, whoa, I'm not really super sure. But yeah, fingers crossed this weekend I should be able to get another stream in. So again, thank you all, and I will see you soon.